All right, diving in today, folks, we're looking at something pretty wild, how AI can create not just, your average short video clip, but long multi-scene videos. Like think a minute or more actually tell a story, and a good one at that.
Yeah, that's a really ambitious goal in video generation. It's one thing to get a few seconds of coherent visuals, have a whole narrative play out with all the complexities of a storyline. That's a whole different ballgame.
And when you look at the current landscape, there's a bit of a bottleneck, you could say, right? Like we have these awesome transformer models that are super powerful for understanding relationships and data. But when you apply them to a minute-long video with tons of frames and details, they kind of get bogged down.
It's the classic problem of scale. Transformers rely on this mechanism called self-attention, which is brilliant for grasping how different parts of a sequence connect to each other. But the computational cost of that attention mechanism, it grows quadratically as the sequence gets longer. So for a 1-minute video with, say, 30 frames per second, you're talking about 1,800 frames. The sheer number of calculations involved in attending to all those relationships becomes, well, frankly, impractical.
Exactly, like trying to juggle 100 different things at once, something's got to give. And that's where researchers have been turning to more traditional architectures like recurrent neural networks or RNNs. They're a bit more efficient at handling long sequences because they process information step by step. And they have these newer variants with linear attention mechanisms like Mamba and DeltaNet that are even more efficient. But, and this is the crux of the research we're diving into today, even those advanced RNNs seem to hit a wall when it comes to generating videos with really intricate storylines and dynamic action.
The problem lies in what's called the expressiveness of these models. Traditional RNNs, they rely on a hidden state, which you can think of as a sort of short-term memory bank, track of everything they've learned from the video sequence so far. Now, the issue is, this hidden state is typically just a matrix of fixed size. It's like trying to cram a whole epic novel's worth of plot twists and character development into a single note card. You just can't capture all the nuances and interconnections that make a story truly captivating. And that's what limits the complexity of the videos these models can generate.
So the memory just isn't big enough or, well, smart enough to hold all the necessary information for a long, involved video. That's where this new research comes in, and it's actually causing quite a stir in the field. It's titled 1-Minute Video Generation with Test Time Training, and it was just accepted to CVPR 2025, which is a really big deal in computer vision.
Oh, absolutely. CVPR is like the Super Bowl of computer vision conferences. Getting a paper accepted there means you got something truly innovative and impactful. And this research, it definitely fits the bill.
So let's unpack what they've done because it's pretty ingenious. For starters, these researchers have set a very specific goal to create 1-minute videos that are not just visually impressive, but that actually tell a complex, multi-scene story with lots of dynamic movement. And, get this, they're using Tom and Jerry cartoons as their test case.
Tom and Jerry. Brilliant choice, really. I mean, those cartoons, they might seem simple on the surface, but they're packed with long sequences of an effect, chases that span multiple rooms and scenarios, all sorts of clever gags that rely on a deep understanding of timing and consequence.
Exactly. It's like a perfect microcosm of what makes long-form video storytelling so challenging. You've got the elaborate chains of events that unfold over time, and to generate that kind of complexity, you need an AI that can truly grasp long-term dependencies. Now, our sources actually quote researchers directly on this expressiveness bottleneck. They say, and I'm quoting here, we believe that these RNN layers generate less complex videos because their hidden states are less expressive. RNN layers can only store pass tokens into a hidden state of fixed size, which is only a matrix for linear attention variants such as Mamba and DeltaNet. It is inherently challenging to compress hundreds of thousands of vectors into a matrix with only thousands in rank. As a consequence, these RNN layers struggle to remember the deep relationships between distant tokens.
That's it. That's the core of the problem. It's like trying to, I don't know, fit all the details of a sprawling, intricate city map onto a tiny postage. You might get the main streets and a few landmarks, but all the intricate alleyways, the hidden connections, the stuff that really gives the city its character, that's all lost.
Right, and those hidden connections, those are the long-term dependencies that really make a story, or video in this case, compelling. So how do these researchers break free from this limitation? They introduce this new concept called test time training, or TTT, layers, which seems to completely change the game when it comes to RNNs. What's the big innovation here, the secret sauce that makes TTT layers so much more expressive?
It all boils down to what they do with the hidden state. Instead of sticking with a fixed size matrix, the hidden state itself, a neural network. More specifically, they use a two-layer multi-layer perceptron, or MLP, which they call TT-MLP. And this is a game changer because now, instead of just storing information, the hidden state can actively process and learn from it.
So it's like the hidden state went from being a passive storage unit to like an active learner, right?
Exactly. It's like giving the memory a brain of its own. It can analyze patterns, adapt to new information, and build much more sophisticated representations of the video sequence. And this is where the test time training part comes in. Even during the process of generating a new video, which is technically test time for a neural network, the weights of this hidden MLP are being updated. It's like the model is constantly fine-tuning its memory as it goes along.
That's fascinating. So it's not just recalling what it's seen before, it's actually learning from it as it generates the video. Our sources highlight a passage from the paper that explains this really well. Let me see, here it is. The key idea in 43 is to make the hidden state itself a model for dollar with weights W dollar, and the update rule a gradient step on the self-supervised law cell dollar. 4. Updating the hidden state on a test sequence is equivalent to training the model $5 at test time. This process, known as test time training, TTT, is programmed into TTT layers.
It's pretty mind-blowing when you think about it. It's like the model is constantly analyzing the video it's creating, figuring out how to improve its own understanding as it goes along.
But what exactly is it learning? What's the goal of this self-supervised training that's happening within the hidden state?
Good question. So in this specific implementation, the hidden MLP is trying to reconstruct a projection of the current input token. Think of it like this. The model sees a frame of the video, it extracts the most important features from that frame, and then the hidden MLP tries to predict what those key features will be. And by comparing its predictions to the actual features, it adjusts its weights, essentially to represent those features more accurately.
It's like it's playing a game of guess what comes next with itself and getting better with each.
Precisely. And by playing this game, it's building a much richer, more nuanced understanding of the video's visual content and overall flow. It's no longer just storing information, it's extracting meaning and patterns from it.
Now, you've mentioned this idea of an inner loop happening within each TTT layer, but you also mentioned an outer loop. Could you clarify what these two loops refer to and how they work together?
Of course. So the outer loop is the traditional training process that you'd apply to any large neural network. This is where you feed the model a massive data set of videos and their corresponding text descriptions, and it learns the general principles of video generation. It's like giving the model its basic education in filmmaking. Now, during this outer loop training, the TTT layers are also being trained, but they have a slightly different role.
And that different role brings us to the inner loop, right?
Exactly. The inner loop is the test time training that happens specifically within each TTT layer. So while the outer loop teaches the overall models how to generate videos, the inner loop allows each TTT layer to personalize its understanding to the specific video it's currently working on. It's like taking those general filmmaking skills and then applying them to a particular genre or style.
So the outer loop sets the foundation, and the inner loop allows for specialization. I like that analogy. Now, the researchers took this clever TTT layer and plugged it into a pre-trained diffusion transformer model called cogvideo-X5B. This is a really powerful model in its own right. What were the key architectural considerations when it came to integrating TTT layers into this existing framework?
Right. So using a pre-trained model like cogvideo-X is a huge advantage because it already has a wealth of knowledge about video generation. But you can't just shove in a new component without potentially messing things up. What they did was strategically place these TTT layers after each self-attention layer in the transformer. But they also added a very clever mechanism called a gating mechanism.
Okay, gating mechanism. Tell me more about that. What's its purpose?
Think of the gate as a sort of volume knob for the TTT layer. Initially, this gate is set low, so the TTT layer's influence on the output is minimal. But the model trains on the Tom and Jerry dataset. It learns how to gradually increase the volume, allowing the TTT layer to contribute more and more to the final video. Smooth transition that prevents the TTT layer from overwhelming the pre-trained model's existing capabilities.
So it's like gently introducing a new instrument into an orchestra rather than just blasting it at full volume right away. Makes sense. Now, there's a bit of a conceptual clash here that I wanted to touch on. Cog Video X, being a diffusion transformer, operates non-causally. That means it can look at the entire video sequence, past and future, when generating each frame. But TTT layers, because they're based on RNNs, are inherently causal. They process information in a strict forward direction. How did the researchers reconcile this fundamental and how these two components process information?
This is a really insightful highlights one of the more technically challenging aspects of their work. To bridge this gap between non-causal and causal processing, they came up with this ingenious technique called bidirection. They basically apply the TTT layer twice, once to the original video sequence, going forward in time, and then a second time to the same sequence but in reverse order, going from the end to the beginning. And then they cleverly reverse the output of this reverse processing. So now they have two sets of representations from the TTT layer, one capturing the forward context and one capturing the backward context. And by combining those, they can essentially give the TTT layer a sense of the full temporal context, even though it's still processing the sequence one step at a time.
Ah, I see. It's like giving the TTT layer a sneak peek at the future without actually violating its causal nature. Very clever. Now, the choice of the Tom and Jerry dataset seems quite deliberate. Can you talk a bit about why this particular dataset was chosen and how it was used to achieve this impressive feat of generating minute-long coherent videos?
Yeah, the choice of Tom and Jerry was really strategic. As we discussed, those cartoons are chock full of complex action sequences, multi-scene narratives, and all sorts of shenanigans that really test the limits of long context video generation. And for their data set, they specifically focused on classic shorts from the 1940s, about 7 hours worth of material. But what makes this data set especially powerful is that they didn't just use the raw video. They had human annotators create detailed text storyboards for each cartoon, breaking them down into 3-second segments and painstakingly describing the background, the characters, their actions, the camera movements. It's like having a super detailed script for each time the cartoon.
Wow, that's some serious annotation effort. So they had these mini scripts for every 3 seconds of the cartoon. How did they use that to actually train a model that can generate much longer 1-minute videos?
Right, so they took this insensitely rich data set and applied a multi-stage fine-tuning strategy. They started by finding the entire Cog Video X model on those short 3-second segments, teaching it the visual style and narrative conventions of Tom and Jerry. During this initial stage, the TTT layers and their associated gates were allowed to learn more rapidly, adapting to the specifics of this new domain.
So the model's getting a crash course in how to think like a Tom and Jerry cartoon. What happened next?
Then they gradually increased the length of the video segments they were training on, first to 9 seconds, then 18, then 30, all the way up to 63 seconds, which is just over a minute. And during these later stages, the focus shifted to primarily fine-tuning the TTT layers and the gates, while keeping the learning rate lower. This allowed the model to progressively build its capacity for handling longer and longer dependencies, without forgetting the general knowledge it had acquired in the earlier stages.
So it's like slowly stretching the model's ability to remember further and further back in time. But I imagine there's a computational cost to this. I mean, we're talking about neural networks within neural networks here. How did the researchers address the efficiency challenges of this approach?
That's a crucial point, and it's actually where they made some of their most significant academic contributions. One of the key challenges with TTT layers is that because the hidden state is itself a neural network, each update step requires running back propagation through that entire inner network. That can get computationally expensive very quickly, especially for long sequences. So to tackle this, they introduced something called inner loop mini batching. Instead of updating the hidden MLP after processing each individual token in the sequence, they process a small batch of tokens together, typically 64 of their implementation, and then perform a single update for the entire batch. This allows for much more efficient parallel processing.
It's like applying the classic mini batching technique that's used in standard neural network training, but now it's happening within the hidden state itself. Smart. Was there anything else they did to boost efficiency?
Yes. Their second major contribution was a really deep dive into optimizing the implementation of these TTT layers for modern GPU hardware. They specifically targeted NVIDIA Hopper GPUs, which are known for their parallel processing capabilities. Did some really clever things with memory management, sharding the weights of the hidden MLP across the GPU streaming multiprocessors, SMs, and leveraging the super-fast on-chip shared memory, SMAM, to minimize data transfer bottlenecks. They even borrowed some tricks from Flash Attention 3, a state-of-the-art attention mechanism, to further optimize the computations and reduce latency.
Wow, that's getting into some pretty deep technical territory, but it sounds like they really went all out in squeezing every ounce of performance out of these TTT layers. So after all that effort, what was the payoff? How did TTT-MLP actually perform when it came to generating these challenging one-minute Tom and Jerry cartoons?
Okay, so to evaluate their model, they conducted a very rigorous human evaluation study. They had human evaluators compare videos generated by TTT-MLP with videos generated by several other state-of-the-art methods, including Mamba 2, gated DeltaNet, and a sliding window attention approach. And these comparisons were blind, meaning the evaluators didn't know which method produced which video.
So it's a true test of how well these different methods stack up in terms of generating videos that people actually find compelling. What did the evaluators look for?
They rated the videos across 4 key dimensions: text following, which means how accurately the video matched the provided storyboard; motion naturalness, so well smoothly and realistically characters and objects moved; overall aesthetics, just a internal sense of how visually appealing the video was; and, importantly, temporal consistency. This last one looks at how well the story flows, both within scenes and across transitions between scenes.
So it's not just about generating pretty pictures, it's about creating a video that actually tells a coherent and engaging story. And how did TTT-MLP fare in this head-to-head comparison?
The results were impressive. TTT-MLP significantly outperformed all the baselines across the board. They used a sophisticated ranking system called the ELO scoring system, which is often used in chess and other competitive games, to compare the models based on these pairwise evaluations. And on average, TTT-MLP scored a whopping 34 ELO points higher than the other methods. The biggest improvements were seen in temporal consistency and motion naturalness, which really highlights the power of those expressive hidden states to capture those long-range dependencies and generate videos that feel more coherent and realistic.
That's a pretty substantial margin of victory, but were there any areas where TTT-MLP struggled or any limitations that the researchers acknowledged?
Yes, and to their credit, they were very upfront about the limitations. While TTT-MLP excelled at generating these one-minute videos, it wasn't always the best performer for shorter sequences. For 18-second videos, one of the baselines, gated DeltaNet, actually did a better job. This suggests that for shorter contexts, the added complexity of TTT-MLP might not be necessary, and simpler models can still hold their own.
So it's a trade-off between expressiveness and efficiency, which makes sense. Were there any other limitations?
Well, despite all their optimization efforts, TTT-MLP is still computationally more demanding than some of the more streamlined linear RNN models, especially for very long sequences. And while the generated videos were significantly more coherent and natural than those from the baselines, they still occasionally exhibited some of the artifacts that are common in video generation models. Things like objects morphing in unnatural ways, or slight inconsistencies in lighting between frames. The researchers point out that these artifacts are also present in videos generated by other state-of-the-art methods, so they might be partly due to limitations in the pre-trained CogVideoX model itself.
So it sounds like there's still room for improvement, both in terms of computational efficiency and addressing those visual artifacts. What directions do the researchers see for future work in this area?
They outline several exciting directions for future research. One key area is to further optimize the implementation of the TTT-MLP, maybe even at a lower level, by tweaking things like the way instructions are ordered on the GPU, or how memory is allocated. That could lead to even better performance. They also suggested exploring different ways to integrate TTT layers into pre-trained models, maybe experimenting with different architectures beyond diffusion transformers, like autoregressive models, which have their own unique strengths. And perhaps the most ambitious idea they put forward is to explore using even larger and more complex neural networks, maybe even transformers themselves, as the hidden models within TTT layers. That could potentially open the door to generating even longer and more sophisticated videos, maybe even feature-length films with intricate plots and characters.
That would be incredible. It really feels like we're on the verge of a whole new era of video generation, and these TTT layers are a key part of making that happen.
I completely agree. It's a really exciting time to be working in this field. And for me, the most fascinating takeaway is this idea of learning within the forward pass. The fact that a neural network can adapt and tune itself on the fly while it's actually generating a video or processing some other kind of sequential data, that opens up a whole new world of possibilities, not just for video, but for all sorts of AI applications.
I can imagine this having a huge impact in areas like natural language processing, where you want a model to be able to dynamically adjust its understanding of a conversation as it unfolds, or in time series analysis, where the patterns in the data might be changing over time.
Exactly. The implications go far beyond just creating cool videos. This is a fundamental shift in how we think about AI learning and adaptation. And what's even more exciting is that this is still early days. The researchers are already working on improving the efficiency and capabilities of these TTT layers, so I think we can expect even more breakthroughs in the near future.
Well, on that note, I think we've reached the end of our deep dive for today. A big thank you to you for bringing these fascinating sources to our attention and for walking us through all the technical intricacies. And to you, our listener, we hope you found this exploration of 1-minute video generation with test time training as mind-blowing as we did. Until next time, keep exploring.